usual for a faculty member that every year we have a fresh set of people to whom give lectures. Nevertheless, there has been a lot of development also since I last spoke to you on Industry 4.0 protocols. For here, this is for manufacturing because I have made it specific to manufacturing and removed the reference to railways also as because this is general technology. I have about 50 slides, so my duration of my lecture would be about 45 to 50 minutes. And if you have any questions, I'll be very happy to answer those questions. And we can interact after that. What happened? Yeah. So the objective here, this is in the context of a specific project that we had taken up under the technology mission for Indian Railways with the help of Department of Science and Technology and the Department of and the Ministry of Human Resource Development at that time, now the Ministry of Education, for implementation of Industry 4.0 protocols for the modern coach factory at Raebareli. And the idea was that we should be able to improve productivity in terms of better utilization of resources, deliver better quality, and obtain flexibilities in the processes of manufacturing and assembly. Before talking of the project, let me first discuss a little bit about what exactly is Industry 4.0 and how do we interpret that. So this is Industry 4.0. It is not as if the world did not exist before Industry 4.0. Industry 1.0 refers to the first industrial revolution that happened in the year 1760 to 1840. That is the time period that is assigned to the first industrial revolution. This is the to give you a reference in time in India. This was the time of the end of not really the end of the decline of Mughal Empire in India, where India was still in a very, very feudal state of existence, and that the Europe underwent the first industrial revolution through the invention of steam power. Steam power had its consequences. This was the invention of the steam engine by James Watt and has had its consequences on textile manufacturing, which was the first to adopt these changes, as well as iron industry, agriculture, and mining in England. The second industrial revolution is just after the time when we were fighting our first war of independence, 1870 to 1914, and this is when the rail network and the telegraph network was laid out in Europe. Even more present, electricity, which allowed factory electrification and modern production line. So railroad networks, which were laid out during this time, as well as the invention of electricity and telegraph, which allowed faster transfer of people, faster transfer of ideas, electrification of factories, and the laying down of a modern production line. Production lines did exist for handicrafts, for agricultural produce in India as well as in other countries, but its electrification started taking place during this period. This is referred to as Industry 2.0. Industry 3.0 is late 20th century, which is also called the digital revolution. And this is marked by the advent of the digital computer. Different types of digital computer, different capacities of digital computer, which enabled faster communication, faster calculations, and gave an impetus in many ways to propelling science and technology in in an in a much faster accelerated mode. This is Industry 3.0. Industry 4.0 is a term which was first coined in the year 2011 uh, in the industrial fair at Hanover in Germany, and uh, is being called as Industry 4.0. Now, what does this really mean? Uh, it promotes computerization of manufacturing, strong customization of products under conditions of highly flexible mass production. It is basically, broadly speaking, it is Internet of Things. It is Internet of Things. It is connecting machine to the cyberspace to man, man to man, man to machine, and machine to machine. This kind of connectivity, which is now possible through the cyber physical technologies that have been developed. Integration of uh, integration of all these players who take part in either a production process or uh, in any other technology activity. Maybe it may be scheduling, it may be mining, it may be water management. So it promotes computerization of manufacturing, strong customization of products under conditions of highly flexible mass production. And since now computer and cyber activity is linked to the physical activity, you have uh, uh, you can put methods of self-optimization, self-configuration, self-diagnosis, cognition, intelligent support of workers, uh, and the workspace becomes increasingly complex. The four design principles of Industry 4.0. One is, and these are the pillars of Industry 4.0. They are interconnection. The machines are interconnected to each other, like a milling center would be connected to any other machining, say a welding robot. Uh, they are talking to each other through sensors. So I may have one machine in a shell shop, the other machine may be in the wheels and axle shop. They're talking to each other. I would have, and machine also means trains. You have one train talking to another train without the involvement of uh, of any human being. Okay, that is quite possible. It does not need elaboration now. So interconnection between machines, sensors, people to interconnect and communicate to each other via Internet of Things. and Internet of People. We will see in slightly more detail what does it involve. So once you have interconnection, there is obviously transparency of information. Whosoever has access to the platform on which this interconnection has taken place, and whosoever you wish to give access to, you can provide transparency of information to operators, to managers, to heads of organization. All the useful information can be processed online, and it automatically gets delivered, and it is visible to whosoever you wish these this information to be visible to. Technical assistance can be provided wherever necessary by through human intervention or through artificial intelligence. Right, human intervention, like you can if uh, is like sitting here and in Bangalore and controlling our mission to Mars, controlling the Mangalyaan from here, and uh, we have that capability in certain areas. We have that capability in space. We have that capability in the nuclear domain. We have that capability to a very great extent in aerospace systems, and uh, we should try to develop similar capabilities in the railway system as well. So technical assistance can be provided either through human beings or through artificial intelligence wherever it is needed, and also perform unpleasant and exhausting and unsafe tasks for human workers, like cleaning up some of the mess in the nuclear power plants where it is not possible and it is too risky. Why nuclear power plants? Even hospitals, uh, they are using robots for unpleasant and exhausting and unsafe tasks for human beings. Also, decisions can be decentralized um, depending on where whom you assign the decision making power to on your platform. Yeah, any questions? Okay. So, so the scope of this project was to use Industry 4.0 techniques and technologies to provide insights into the manufacturing and assembly processes. Our Prime Minister, when he visited MCF, he those days the production was about 700 to 800 coaches per annum, which was ramped up to say 1500, 1200 to 1500 coaches through bits and pieces implementation of Industry 4.0 principles. He made an announcement during his visit in 2018 that the production be increased to 5,000 coaches per annum. Though 5,000 coaches per annum is not an unrealistic not an unrealistic aim given the infrastructure at modern coach factory Raebareli. 3,000 to 4,000 is eminently possible without too much of a problem. Uh, but unfortunately, after this project got initiated, the objectives got changed because of the COVID circumstances, where the increase of production that was initially envisaged was did not remain that high. But still, the technology has been developed, and the technology which has been developed through this project through government support now, defense is interested in implementing this um, for for the factories for where Bofor's gun is being produced, and for small arms and pistols and handheld guns. Uh, this technology is being implemented for the manufacturing. These are separate projects though. There is a lot of interest shown in this platforms that have been developed by the mining industry, both India and abroad, and also in the infrastructure sector. I'll show you what is so typical and so indigenous about this effort. Uh, so the scope included providing insights and improving the productivity, automatic scheduling and planning, real-time monitoring of the health of the assembly line, because then now you have the machines talking to a platform, and then uh, development of artificial intelligence and deep learning techniques to improve overall productivity. Uh, it is also important that the control over the operational and intellectual aspects of these technologies, especially these technologies, has to be indigenous, and the control on the data, the ownership of the data, the ownership of the technology has to be that of Indian Railways. It should not happen that our data uh, is gets since it's a platform, and whosoever develops the platform has the data. The data for manufacturing, even the data for scheduling, if you want to do scheduling of trains, timetable scheduling of trains, scheduling of other operations like wash line operations and other operations. If the data is on the platform, then you should not have a girl sitting in Malaysia dictating to you what you should produce and what you should not produce, and what machines you should buy and what you should not buy. This started happening when we carried out our initial negotiations for collaboration and implementation of some of the platforms that that people claimed that they are available, but they did not have a solution to our kinds of problems. Secondly, if they had a solution, uh, it was like a coffin which was of a fixed size, and uh, they wanted our dead body to be cut into the size of their coffin. It is, it is most of the time it is like that with uh, certain platforms that we import, that they have a format, and uh, the format for a solution, they have a solution, but they want us to define our problem in such a manner that their solution fits our problem. Now, the technology context of cyber physical systems it involves Internet of Things. It involves system design and dynamics. Uh, we also had a component of design where coach design and coach dynamics had to be understood. It involves manufacturing processes, quality control, sensors, data acquisition, signal processing, neural networks, optimization for reliability, availability, maintainability, and sustainability, RAMs. All these domains of technology in 4.0. The idea is to move from Internet of people to uh, Internet of Things. Uh, just one slide on this background aspect. You have Internet everywhere. It is primarily a connection between people. I'm talking to you, and I'm talking to you through the internet. So it is one person, that is me, connecting to you, 10 persons or 50 persons over the internet. So it is internet of people. We are talking about internet of things. Internet of things, where one thing meaning it can be an inanimate object, an object without life, like the table that I am sitting on, the table that I'm sitting at, and the chair I'm sitting on, and they start talking to each other without my intervention once they are sensorized, uh, or a chair here in on which I am sitting starts talking to another table in Timbuktu through the internet. So if the table says something, the chair starts moving here. Uh, that is the kind of uh, technology that is, that is what is meant by Internet of Things. So earlier you still have people connecting with things through the ECG sensor, like through a motion sensor. It can all be, this data is already being collected by your smartphone, and you can send it over the internet to a hospital, to other places, and to your uh, Facebook, wherever you wish. This was not possible. This was not possible, not imaginable, even 10 years ago or 5 years ago, that I and my parameters would get connected to the rest of the world through internet. Now, things connecting with things, like this car talking to the petrol station, gas station, uh, car talking to the workshop while it is moving on its own, conveying its own parameters, like accelerations, pressures, temperatures, so on and so forth. A normal, respectable car these days, advanced cars, I'm not talking of, pardon me, nano car, but any decent car worth its name has about 100 sensors these days. It has at least 4 kilometers of wiring, and now this wiring is also being done away with a wireless connectivity between different sensors in a modern car, and they are all communicating. If you wish, they will all communicate with a platform through the internet, and then you can do whatever you wish about it. Even in the railways, if you have once you start sensorizing your coaches and wagons and bogies with sensors, just imagine the amount of data that is going to flow in. You have 10,000 passenger trains, you have 8 to 9,000 goods trains, you have 10,000 railway stations, and with so many other features, 67,000 kilometers of active track. If they all start communicating data, just imagine the amount of data that gets communicated, and how do you store that data? How do you process that data? Whether you need that data or you don't need that data is a question. You obviously need the data because you wish to improve the efficiency. Wish to improve the productivity. You wish to decrease human drudgery. You wish to make the operations safe. You need the data. You need then a lot of data processing to be done. You need a lot of data compression needs to be done. A lot of intelligence needs to be extracted out of this. आवाज आ रही है आपको? आवाज आ रही है?
Yes, sir. You're audible, sir. Absolutely
Okay.
audible, sir.
So, so that is why when they say that we have a lot of work to be done by our own scientists and engineers within our own country. Our scientists and engineers, yes, our scientists and engineers are doing this for outside countries. But there's a lot of work that needs to be done within the country itself, and within railways itself. There is a huge scope for such work. So what is stopping us? There are certain things that I will come to later. What are the bottlenecks? Uh, just one more slide on Internet of Things evolution. So you had the pre-internet fixed mobile telephony, where you were sending, where you one was talking to people over handsets, over telephone sets, and was sending in SMSs. We were restricted to SMSs. So this was pre-internet days. Then Internet of Content, www, email, information exchange, entertainment also started through Internet of Content. Then Internet of Services, e-productivity, e-commerce. This was a stage of development. Then through smartphones and applications, where your phone became a TV, where your phone itself became a post box, where your phone became a camera, your phone became a temperature sensor and an acceleration sensor, and practically everything. Through Skype, YouTube, and Facebook. And now we're talking of Internet of Things, identification, tracking, monitoring, metering, all these things through the internet, but through certain basic requirements that need to be fulfilled if we were to achieve this. Now, I will talk about the bottlenecks and uh, the work that required to be done in the context of this plant layout of modern coach factory. This is a highly compressed, um, highly compressed photograph of this shell shop. This is the shell shop. There are 8 to 10 such other shops in MCF, wheels and axles, and then paint shop, furnishing shop, electrical shop, and so on. We have very good infrastructure. In fact, it is much better than the infrastructure that I have seen in many European countries and even uh, Korea and China. Uh, this is really state of art. This uh, one single shop has huge space. This would be about 800 meters, and this is about 200 meters. Not from here to here to here. Okay, the size of a football field is 100 by 100. So here material enters from this side. These are various bays and various workstations, various bays and workstations. So there may be one route for, say, underframe. This may be for end wall, side walls. In between somewhere, it may be for for the toilet. Then roof. In total, there would be about 100 odd machining stations in this area, including machining centers, welding robots, etc., etc. And once they travel from here to here, this is the assembly shop. This is the assembly shop. This is where the assembly takes place. Now, at any instant of time, if you say you are processing, you have orders for, say, 10 coaches, you would have, and these 10 coaches may be of different makes, maybe for Vande Bharat, maybe for Shatabdi, AC 3 tire, and so on and so forth. So different components, different makes or different variants of coaches. Each coach roughly, broadly, would have approximately 3,000 components worth taking note of. And though we are just making 10 coaches in, say, in a given order over a period of 2 to 3 days or 4 days, the inventory that might be lying around would be for, say, 25 coaches, a minimum of 25 coaches. And it is not a straightforward flow of the components from so if this is one machining station, this is another machining station, this is third machining station, fourth machining station, 5. And then a component may start from here, go here, and then go here, then go here, then go here, and out. So each component has its own process flow, and large number of these components, large number of these machines. The big problem is in implementation of uh, Industry 4.0 and making the machines talk to each other is that each machine talks in a different language. You have a machine from Siemens. It talks, it has its own controller. So it will talk in the language that has been prescribed by that controller. It will talk only in German or the controller language. You have robots which are Fanuc robots. And in Siemens also, there will be different types of machines. Some machines have controllers which are recent, some machines which have controllers which are old. Some machines have do have controllers, but the vendor has not given the software through which you can take out the information. So if it is talking, machine is communicating, it is communicating to its own console. It is talking to its own self. So different makes of machines with different controllers. You would have Fanuc robots and Fanuc machines which have their own different controllers. They talk in a different language. You have Heidenine machines which again have their own language and they're talking to themselves. You have machines which are completely dumb. They are not instrumented at all. They have no sensors whatsoever. They are manual machines and they don't talk whatsoever, but play a very important role in the manufacturing process. And there are a large number of such machines. How do you make them talk? So the biggest problem in any manufacturing plant, which is a legacy plant, and even if it's a modern plant like MCF, the problem is more acute in Kapurthala and in older factories, the one in Chennai. Mm, Here, they talk in different languages. If I were to start a new plant altogether, then I can have all the machines from Siemens, and then there is no problem. I can simply go and implement whatever automation that they suggest. But then I have to be dependent on what they decide for us. If it's a completely greenfield factory, if it's Alstom, then you can do it for that. But for systems which are your own systems and which have developed over a period of time, and we mostly have these systems, this is the problem. This is the basic problem, that you have different machines which talk in different languages. The same is true for your the sensors that you are putting in coaches, and yeah, the sensors that you're putting in coaches. And this is what I had been insisting earlier also with uh, the member Rolling Stock uh, when he was there, that you have one sensor system from one vendor, and you have another sensor system. Maybe this may be for bearings, another one may be for axles, the third one may be for HVAC. different different vendors, different systems, and they have their own sensors. So this fellow will put one server, this fellow will put another computer, this will put another computer, and and they are not talking to each other. There is no communication amongst these uh, these boxes. So you have 10 different boxes which cannot talk to each other. The temperature information cannot be connected to the vibration information, and it cannot be integrated over the entire train. If it remains within the coach itself, within the wagon itself, it would remain there because it is not scalable. This scalability issue is one issue that one needs to address. You need a common protocol for all these sensors to be talking to, where they can communicate, where they can communicate the raw data. Now, these sensors that the vendors supply, they do not give the um, the raw data. They give processed information. This is a problem that we were facing, that I was discussing with the DGRDSO just the day before yesterday, for the instrumented wheel, that they are not giving us the raw data. They just give us processed data, which will light a red button, or a green red bulb or a green bulb. It would light whether it is good, bad, or ugly, and uh, we don't get the raw data, and most of the time their calibration goes wrong. So this is the biggest bottleneck in implementation of Industry 4.0. So we have tried to solve this, and we have succeeded in a big way in this particular project, that we have designed a platform where we can access data from practically all the machines, all types of controllers, and also, in addition to that, if there are these components, like this is one sheet which is traveling from one end to another. You put an RFID tag. You put an RFID tag, and there has to be a RFID reader as well. So there is an RFID reader here. There is an RFID reader here. There may be another one here. So as the particular component travels from one end to the other, these RFID readers should, should also should also communicate data to the same platform, so that along with the machines we have component information as well. Then you would have yes, yes. Acha, may I request you to mute yourself if you're not asking any question, because I get the impression that you are asking me a question.
No, sir. Perhaps it was by mistake, sir. I have muted.
Okay. So along with the machines, the components, the machines have to, this is the machine, the machine has to send data. The component has to send data through these RFID readers that I have drawn. And then there is also, I'm drawing that in another color. You have an operator here, a person here, a person here, maybe a person who is roaming around. They will be carrying pads or their own industrial HMIs, human machine interfaces, which will be a pad which will which will carry their thumb impression or Aadhaar card number, and if they are at a particular machine or working station, they would key in the data of uh, when is the component got in and when has it got out, and all the relevant information about his own action. That also has to communicate to the same platform, and this can be done for a variety of applications like inspection of tracks and so on and so forth. Where but the you should have a platform which can listen to listen to all this data which is streaming into it, and present it in the form of an Excel sheet or do whatever you wish. And then within this platform itself, you write your algorithms for optimization, for decision making. So the hardware is not important. It is this platform creation that is important, which can not break into these codes. These individual controllers can be negotiated by this code and present the data. Let me go forward from this slide. So this is the process flow. This is the process flow for the sidewall, the roof, how it goes and how it gets assembled, end wall, under frame, etc. So this needs to be digitized, and we create a digital factory. So the architecture is like this. It is this is architecture, not proposed. It has already been done. You have one numerically controlled machine, another numerically controlled machine, non-NC machine, machine N. This is the shop floor, and they all communicate on the same platform like this, where on top of that you can do scheduling, health monitoring, product life management, ERP, and any other analytics that you can build because you have written your own code. And all this has been done in an open source platform called Python, which is the latest and the state of art. And the cost is practically no cost, because uh, what the kind of quotations that we got from, I would not like to name the vendors were of the order of about 200 to 300 crores for the factory, and for a uh, single shop it was of the order of 20 crores. Just for making a visit they wanted 2 crores. Now this we have developed, our development cost itself has not been more than 5 crores, and now it is free for implementation anywhere in the railways. And since it has been developed through the mission, we don't take any consultancy costs also in this. This is all for purely a professional exercise, which we thought was important to be done for the country. So you can fetch third-party data from here. You can load your own control programs. It's basically written in Python, and those of you who have seen Anaconda in Python, it has so many libraries that now you can probably do whatever you wish on uh, on the on the platform. You can develop your own Industry 4.0 platform. Many youngsters in especially in IRIMEE would be so qualified that they should be able to do this on their own also. So networking involves a fiber optic network. This is required. In MCF, this is present. Uh, in ordnance factories and the defense productions, some of these factories, shop floors, they are not present. So we first start with laying down the fiber optic network. If and then wireless network is also supported on top of that, but fiber optic is essential. One centralized server is sufficient, and a centralized data bank, and then a set of other servers act as the backbone. Uh, so the normal networking and data logging techniques, but it has to be done. Uh, Writing and doing it and making it work, it takes time and effort. Uh, but once you get started in this domain, uh, you will develop your own experts also who should be able to take care of the entire system. What is the format in which you require data? What is the format you require standard data? What is the frequency in which data is required? Whether you want it 10 samples per second or one sample in 10 seconds, different sampling frequencies for different types of data. Then schedule optimization is I will talk about it slightly later. I will be able to finish it in another 10 to 15 minutes. So we will do schedule optimization. Then these kinds of indicators, inefficiency come utilization indicator, productivity indicators can be built. I'll just show you samples for the machine shop, for plant, and what is the status of current orders, what is the capacity to cater to future orders, how much capacity is left, and if there are uh, requirements in terms of expansion of infrastructure, those indicators can also be obtained. Uh, Health monitoring. Monitoring is now quite a regular activity. In India, we have many experts within the country in the area of condition monitoring, whether it's aerospace, power plant, automobile. A lot of monitoring algorithms are available within the country itself in academic institutions as well as research organizations, defense organizations, CSIR organizations. Uh, also within the railways, there are a couple of people who are quite adept at this. Uh, Further analytics, etc. All these things uh, can be built because it's a question of software and making predictions. Once you have the data coming to you on the same platform, you can do whatever you wish. You need the data. So far, the most crucial thing, as I uh, emphasized, is that the data should be made available. The data is not available from our machines by the sensorization that is being done by some of the vendors. One has to always insist that they give us access to raw data, not just the processed data. Whether we use the raw data or not is a different question, but the data belongs to the Indian Railways. The control on the data should be that of Indian Railways. It should not be some fellow who is sitting in Hong Kong or Indonesia or France for that matter. Now, the solution, our solution in MCF, I'm coming to the specifics of the solution. You have the Unigraphics NX and Team Center software, uh, from where the design and the component list is provided. The production plan is in some form available. It is not a very regular plan, and not a very centralized information that is available. This needs to be regularized, in fact. Stocks and purchase order status. All these things are there, but in bits and pieces, whether in hard form, soft information, but it is all bits and pieces. It is not as if it is streamlined and centralized. Indent generation activity is there. Materials and stock, there is. So our focus has been on these two rectangles: real-time machine monitoring and this scheduling. And then integrating the two. This has been our activity. And the overall picture obviously includes all this. But in terms of technology, it is in these two rectangles. Rest of it is dependent on local people, how they wish to implement it. Now, this is the dashboard, and I would not give you a live demonstration at the moment. Let me see if I can give you. When I press this, live demonstration will take a lot of time. Otherwise, you'll have to call me some other time to uh, show you how sitting here in Delhi or sitting there in Jamalpur, you would be able to you are able to see the data in Raebareli. So this is the digital twinning process, then real-time monitoring, analytics, uh, machine details, bill of materials, inventory, job scheduling, and a help desk that has been built in. This is a Python dashboard, and this can be implemented on a phone as well as on a laptop. So in the physical world, you have machines, sensors, RFID. Sorry. Oh, One back. So the physical world is communicating to the data acquisition layer, then to real-time monitoring, from where we take the data and store it for a longer time depending on the requirement. Then uh, you have existing ERP and CRM and inventory systems at MCF and CRIS. They, through protocol adapters, uh, that information goes to the scheduling code, and then this goes to the dashboard, and then analytics and modeling and training, all within the same package, same platform. This is done in OPC servers and through empty link I. This for Siemens machines and for Fanuc machines. This is a firmware which these firms provide along with the machinery. So this firmware, sometimes they don't supply it. So we also have to check whether they've given it or not given it. And once the machine is supplied, they don't give it also. They play tough. So it is through this, then all this has been done in LabVIEW. This layer is in LabVIEW. Then this is done in Python. Scheduling has been done in Python, and the entire package is been encapsulated in Python. So apart from Python, you don't need anything else, because even in LabVIEW we convert all the codes into .exe files, and put it in Python. This is a typical system architecture. These are the individual machines, and through their individual firmware, they are being read in the same platform. And then scheduling, production, etc. This is how what the architecture is. Now in the LabVIEW code as well as the Python code, you have to create a digital twin. You have to start keying in the information of every machining center. Like this is one machining center, this is another machining center, this is another machining center. A digital twin has to be created. They are all of different mix. The first thing is to make a digital twin and initialize that. And then you have to identify the operation carried out by each machine on component X, component Y, component Z, component Q, component R. And on one component itself, say component number A, machine number 1 will perform one operation for how much time. Then it goes to machine number 2. What is the material handling time between machine 1 and machine 2? And then what is the operation time? So operation sequence and material flow needs to be identified and defined. This is the most uh, difficult thing to do, because uh, the operational sequence and procedures in any factory in India, whether it is public sector or private sector, is very, very loose. It just flows. It happens, and only the person on the shop floor knows what is happening. So whether this operation should take uh, 5 minutes or 45 minutes, and just depends on it is not defined properly. Most of the cases it is not defined whether the operator has gone for a smoke or has gone to the hospital or to the toilet. It is all dependent on all these things. So when you see uh, this is the dashboard that you would see, and these are for the different machines on the digital. The yellow ones are the ones uh, which are working. Uh, the ones which are off are shown here. This is a snapshot taken some time ago. This is something that I can show you real time also, but it will take time. I have not tested whether I can show it to you right here or not. But uh, when I press on that dashboard, this is here on this dashboard. The different segments are, this shows the instantaneous information of various machines, whether they are working, not working, on, off, whether there's a fault condition, emergency condition or not. You would be surprised to know that, and I'm not being critical, that if you have say 50 machines at any instant of time, you don't have more than half a dozen of them working. While in the rest of the world, such systems and such infrastructure is expected to work round the clock. But our systems, the efficiency and the time is, this is what transparency also does. So this provides the real-time status. This panel on the right-hand side, this panel can be designed, redesigned, but this is the panel at the moment. For every machine, it will show the time history of how long it has been working. Say from 1410 to 1425 is the snapshot for. Then there is RFID tracking. You have information from the component also uh, coming in, that this is the RFID station here, left hand side you can see what time does the component enter and what time does the component get out of a particular station. This information is also there on the same snapshot, on the same screen in fact. This is the kind of coding that has gone into it. This is data acquisition code. And so we transferred this code to MCF. And we also trained their people on how to write the code and what is meant by these different blocks. This is coding in LabVIEW. It is work of nearly 2 years, all done online by research people. This is the screen for optimization, initialization uh, of the OPC network, initialization of this is the code which has been written. Back panel. So for empty link I and these digital environment initialization codes. Then similarly for material tracking, this is the scheme for tracking. This code is also working, but RFID tags are not very useful in an environment which is heavily metallic. So HMIs that I'm going to describe in the next slide are more useful. We have given up on RFID tagging in the environment which is heavily metallic and which requires heavy investment in terms of tracking machines, which are not very reliable always. But the platform does have the capability to take in RFID tag information. This is a human machine interface, and this is what is very critical with the operator. And this is a 7-inch rugged tablet. You either provide this or you have an industrial PC which can be permanently fixed onto the machine. This has found good interest in mining applications where you have excavators where you can put the uh, um, bigger screens and put the make the controller talk to that device there. And this is the operator device, so where again you can we are preferring a Windows based device, not an Android based device. So where personal identification, machine information, component identification, time in, time out, whatever details that are required, and they are uh, sending information to this platform. So the operator, whether he is moving or mobile or immobile, he carries this with him. And this goes to real-time monitoring and scheduling. I will give you the what is describe a little bit about scheduling and then stop there. Scheduling requires plant layout, shift calendars, material flow, typical duration of operations, PSL and part numbering systems, current stock levels, uh, pricing, and lead items for stock items so that you can make buy or make decision. This is a very, very critical decision that needs to be made. The buy or make decision. So the pricing is important there and the lead time is important there. Current stock levels, indent and PO formats, PO status monitoring. It requires all this. Uh, the advantage is that since you're writing your own code and on a platform like it can be done on MATLAB also, it can be done in C++, C Sharp. The Python, the advantage is that it is quite smooth and you can do whatever you wish on that platform. So a typical order in MCF comes in this form. What is the product that is required? Product meaning whether it is Vande Bharat or AC3 tire, the product or any other variants. There are 2 dozen such variants. Quantity, how many coaches are required? 20 coaches, 30 coaches, 40 coaches. When do we start? Start today, tomorrow, day after tomorrow. And what is the due date? After 5 days, 6 days, 10 days. And if there are a number of orders, what is the priority? Whether Vande Bharat has a priority or AC3 tire coach will have a priority. And once I have started the production uh, of these two, there is some other order which would come day after tomorrow or after 5 days, which will say, no, no, this new one has to take priority over the others. So in that case, that becomes a complicated situation and a good mathematical problem also to solve. In that condition, what is the schedule that needs to be adopted? So it has to be done dynamically, and I will show you just one or two examples on with this kind of information. Uh, it also has to account for now when the product has been dictated, you know that these are the components, 3,000 components that need to be made. Out of these 3,000, how many of them are inventory, already available in inventory? So from the extra data file that already exists for these products, you extract the parts, you extract the machines on which the operations need to be carried out, and and the coding needs to be done. that information needs to be sent to components information, and operations also need to be defined, whether it is spot welding or assembly of two pieces together, or a machining operation. So a digital twin and the entire factory gets simulated in soft form, and this is the digital twin of the factory. This is the digital twin of the factory. Uh, so this is a typical Python code where you have virtual machines, virtual components. I'll give you take just one example that I have. I get an order with variant one, uh, say Vande Bharat. Variant two is AC3 tire. This may be Shatabdi, and this may be some other thing. 10, 10, 15, 20 of them are required. The first one has a priority 1, 2, 3, 4. Start date are given here. 12, 6, 21, 10, 6, 21, 15, 6, 21, 16. This is a typical order. This is all done interactively through the uh, through the platform that has been created. The components can be keyed in and keyed out. Everything can be done interactively. So it comes up with these results that the first variant takes 5 days, second variant takes 9 days with this order. With this order, third takes this much time, and fourth takes this much time if we start at the same time. And the code gives you a Gantt chart. This Gantt chart shows that these colors indicate different variants, different orders. So blue is one order, and what operation is being performed for blue from start, what is the start time, end time, and then this red order is taken up, then the green order is taken up, and then the violet order is taken up. Here everything occurs in a sequence. The idea is that there should not be any gap between the operations. It should be as tightly packed as possible so that maximum utilization under ideal conditions take place. If any machine is not operational, as we will see in the next chart, this is the machine loading chart. So for this machine, all these individual machines, which machine is doing what, uh, as you hover the mouse on this, that information also gets displayed on this chart. Now, if there is a problem with one of the machines, that real-time information would come from the real-time monitoring system. So this ideal schedule is continuously in interaction with the real-time monitoring of what exactly is happening to the machine. If the machine is out of order here for some time, or is not functional for some time, then what is the alternate route that needs to be created, or how much time does one have to wait for, and how does the process get affected by the whole thing, uh, or a particular component gets stuck somewhere. All this is gets monitored through the machine loading chart. This shows that if you had not done scheduling, all four of them would have got completed here. Now you have different times of completion of different dates. Uh, Random dispatching versus scheduled dispatching. This is another chart. Uh, Let me talk of scenario two, which is more interesting. In scenario 2, we give priorities and start dates in such a manner that you have some reshuffling that needs to be done. Here in this scenario, you see that you start with blue, then you have to stop because there is some other priority which has come up. You start working with the red. Then you stop that also because there is a third one which has come, which has a higher priority, green. And that also needs to be stopped because the topmost priority is to be started after a few days. So you complete this, then the green resumes, then the red resumes, and then the blue resumes. In such a condition, the in absence of the scheduling, there is a lot of wastage of time because the person does not know uh, how to do the scheduling, what is the best way to schedule it, so as to keep the machine occupied in a comprehensive manner. The whole thing gets completed in the shortest possible time. And this is a problem similar to scheduling of timetable scheduling of trains also. Same thing. Which one to take first and which one to be allowed to take rest for some time. This is scenario 2, and this is in interaction continuously with the real-time monitoring system. This is a machine loading chart, a reflection of the same complicated thing. Here you also see that within this blue itself, if time is available, just see my marker. This green gets taken up. Then this is another interspersion of uh, this type. So we have not yet put we have put some scheduling algorithm here, but this is still not based on deep learning, and this is not there, and neural network also is not there at the moment, but it can be done because there's a lot of experience in deep learning and neural network now. Last couple of slides. Uh, Skip this. This gives you the machine utilization chart. Um, this is quite revealing. If you see that there are some machines like this SH110 whose utilization is quite high, and there are some machines where the utilization is quite low. So it also tells us that uh, if there is a demand for increase in production, uh, and one has to take a decision, then investment on in just this machine, just one more of this would help us clearing the the manufacturing protocol much faster, or maybe investment on just this machine rather than investment on the entire infrastructure is not really required. So instead of one machine here, existing machine, you should have two machines or three machines here. To these are just broad conclusions. There may be other constraints which are not accounted for here, but certain conclusions of this type can be made on the basis of software and analysis of the data that you generate. Similarly, this last slide on the cycle time of production. What is the my optimum production size? By production size, I mean how many coaches should be the manufacturing should go on at the same time. If I do say here, this is just say 3 coaches, let us say, or 5 coaches. Then for each coach, I will take 30 hours. Instead, if I take 10 coaches at a time, then 10 coaches at a time, then instead of 30 hours, I'm going to take 15 hours per coach. So this is a better utilization of my resources and a much more economical way of doing things. However, I flatten out somewhere around 30 or 40. If I do 30 to 40 coaches at the same time, then I take 10 hours per coach. This is quite realistic data and information that I'm giving you. So the capacity of my plant is to do 40 coaches a day, and that is where I flatten out. That is where I flatten out. Beyond that, the reduction in time is not so much. So all this analytics can also be done on the basis of code that one can write. But if it is your own code, you can add to the analytics, you can scale it up and do several other things. So thank you so much. I'm making a pitch for Atmanirbharta in Industry 4.0. This has been my thrust that let us be Atmanirbhar in at least this technology, because we have missed the bus or missed the train in many other technologies that have been developed by other countries. Let us not miss the train and have an Atmanirbhar Industry 4.0 technology in the country. Thank you very much.
Thank you very much, sir. Uh, first and foremost, I wish to inform all the participants of this webinar that our director IRIMEE, Shri P. Ravi Kumar, has joined us for this webinar and is currently available at the IRIMEE auditorium. We welcome you, sir, to this session. Moving forward now, I request the participants to put forward their queries and questions. If you have any, participants of the auditorium, participants who have joined through this online platform. I believe the probationers and some of the awardees at the auditorium, they would have some queries.
Hello.
Yeah. Please introduce yourself. I request to kindly introduce yourself and then ask the question.
नमस्कार, मैं अनिल द्विवेदी, डीन IRIMEE. सर, मेरा एक सवाल था कि in the second or third slide we discussed that with the implementation of this Industry 4.0, we will be able to reduce our dependence on, we will be able to reduce the monopoly of vendors. We will be able to standardize things. But later on, we realized that when we are using machine sensors from different vendors like Siemens and other vendors, they are not able to communicate between them. So my question is there any effort being made to standardize the language for communication of these sensors, as we have done in other things also?
Yes, that has been, in fact.
Sir.
That exactly has been the focus, that we are not dependent on their platform. I do not wish to take any names here, but whatever was being done by one particular specific vendor for one set of machines, one make of machines, we replicate the same screens and same output through this effort, and not just their machines, but for machines of other makes also, RFID. So that has been standardized. We are not dependent on. We are simply not dependent on the software of the vendor that you named. I would be careful about doing that. But we are not dependent. We are not dependent.
सर वो दैट्स ओके, वो तो आपने आगे बताया था. यू आर टोल्ड कि वी हैव डेवलप्ड सर्टेन प्रोटोकॉल फॉर developing a standard interface for getting the information up from all the vendors. My question was different. My question is
Yes,
कि
yes.
in the मतलब in the at the industry level कोई ऐसा हो रहा है क्या कि like we have ISI, some standards organization, we have BSI, some standards are being developed so that all the manufacturers are compelled to develop the sensors which talk in the same one uniform language. At industry level, are some efforts being made?
At industry level, that I would like to answer that question in a slightly different manner. That may not be always possible, because there each vendor has its own history of development. As long as they are willing to give their data to us, as long as they are willing to give their data to us in raw form, the raw data that they are collecting, if they can give the raw data to us on the platform that we provide to them, we meaning Indian Railways provide to them. Indian Railways provides a platform to them that whatever data that you are collecting, whether it is through the onboard diagnostic system or through the air conditioning system, you give us the raw data on this platform. Say a platform on Excel sheet, for example, for a layman's point of view, that if you can give us the data in this form, that is standardization for us. Because all these the sensors and the controllers, they give their output is in the form of voltage and current. Their voltage and current should be readable by us.
Thank you, sir.
That is the level of standardization that one can expect the railways to ask for. That we ask that you give us the raw data, you do whatever you wish, but the raw data should be available on a standard platform, so that if the data of one vendor is required by another vendor or by a third vendor for scaling up operation, our problem is scaling up. We cannot scale up unless we buy all the stuff from the same vendor.
Good afternoon, sir. I am Suman Raj, senior professor ट्रांसलेट at IRIMEE. जस्ट मुझे सिर्फ एक चीज जानना था शेड्यूलिंग प्रॉब्लम के बारे में. नॉर्मली जब दो मशीन्स मतलब 2 मशीन्स अगर इन्वॉल्व होती हैं और सारे के सारे सीक्वेंस अगर उसमें बनाने हैं तो उसके लिए इट इज इजी कि जॉनसन्स एल्गोरिथम यूज करके कर लेते हैं. बट व्हेन इट इज मोर देन 2 मशीन्स और से 10 मशीन 15 मशीन्स, तो उस समय उसका शेड्यूलिंग मतलब कैसे उसका प्लान करते हैं?
वही उसका वर्कआउट करना पड़ता है, प्लान वर्कआउट करना पड़ता है, वो एल्गोरिदम लिखना पड़ता है कि कोई भी मशीन आपका एक ऑब्जेक्टिव फंक्शन आपको बनाना पड़ेगा कि कोई भी मशीन किसी समय खाली ना रहे. ये ऑब्जेक्टिव फंक्शन लगा के जो ऑप्टिमाइजेशन प्रोसेस है, ऑप्टिमाइजेशन कोड लिखा करते हैं. ऑप्टिमाइजेशन जैसे हम लोग पढ़ाते भी हैं, आप लोगों ने भी किया होगा ऑप्टिमाइजेशन का, सिंप्लेक्स प्रोसेस वगैरह. एक ऑब्जेक्टिव फंक्शन बनाना पड़ता है कि ये हमारी कोई भी ऑब्जेक्टिव फंक्शन क्या है, या तो मिनिमाइजेशन ऑफ कॉस्ट होना चाहिए या मिनिमाइजेशन ऑफ टाइम होना चाहिए, प्रोडक्शन टाइम. तो हम उसको किस तरह से करें, कंपोनेंट ए को पहले लें उस मशीन के ऊपर कि कंपोनेंट बी को उस मशीन पे पहले लें, या किसको किधर भेजें. तो वो एक 3-4 ऑल्टरनेटिव्स थ्रो करता है सिस्टम की. ये भी एक ऑल्टरनेटिव, ये भी एक फ्लो पाथ हो सकता है, दूसरा फ्लो पाथ हो सकता है, तीसरा फ्लो पाथ हो सकता है. तो ऐसे 3-4 के अंदर फिर सिलेक्ट किया जाता है कि किसमें पैसा कम से कम लगेगा, या किसमें समय कम से कम लगेगा. जी,
थैंक यू सर.
दिस इज लाइक द सेम वेयर हाउसिंग प्रॉब्लम जो आपने दूसरे फॉर्म में किया होगा कि आपको सामान 10 जगह पहुंचाना है. देश में और 10 आपके वेयर हाउसेस हैं और इतने ट्रक्स आपके पास में हैं, तो उसको किस तरह से शेड्यूलिंग किया जाए कि मिनिमम टाइम में पहुंच सके। एक्चुअली ये फ्लिपकार्ट वाले, अमेजन वाले, इनका सारा जो बिजनेस है दैट इज शेड्यूलिंग बिजनेस, कि किस कहाँ से निकाल के कहाँ डिलीवर करना, कितना फास्ट डिलीवर करना। अमेजोन, जोमेटो, ये सबका दिस इज शेड्यूलिंग इज एट द हार्ट ऑफ इट, एंड engineers they employ who get a package of 50 lakhs, 40 lakhs, 50 lakhs uh, right in the beginning of their career, do only scheduling, logistics, e-logistics and e-commerce, real-time tracking, real-time scheduling, real-time maintenance.
Thank you, sir. Good afternoon, sir. I am Shashwat Gupta, Professor WMT at IRIMEE. Sir, I have one question about on a slightly larger framework. That is to say that, for instance, when we compare ourselves with the West or with Japan, for example, then they have quite a long-term strategy to implement Industry 4.0. And so, for instance, in Japan, we have RTRI's Research 2025, in which they have emphasized on this quite a bit. So, in that same manner, do we have any kind of plan in India to popularize Industry 4.0 in the government?
Well, thank you for the question, but I am not the person to answer this question.
Sir, in that case,
you do need the long-term planning in the country. You should have faith in your capabilities. You should get started and then continue implementing this. We should do it. It is a desirable, but I am not the person to answer this question. But we do assist several other organizations, the other world also, to help in automation, condition monitoring. Just half an hour from now, I have a few professors from an Australian university visiting me on this kind of discussion and talks to be delivered in their university.
Good afternoon, sir.
But yeah.
This is JP Singh. I'm Professor ENHM and IT here. Sir, my question is, we are very new in Industry 4.0 as such. My doubt is, sir, is there any aspect of this Industry 4.0 that also helps us in product development or the capability of product or the outcome? Because it looks like it is everything process related. Why I'm asking this is, doesn't matter how efficiently we make anything, if we are still going to make Ambassador Mark IV, doesn't matter how efficiently, how well we make it, nobody is going to buy it. That was my question, sir. Is there any aspect of Industry 4.0 that helps us in product development?
Product development? No, but there are other aspects, not Industry 4.0 as such, that can help in product development. Product development, for example, if you wish to improve, have a newer kind of a bogie, say 3-axle bogie or a hollow axle bogie, for example, which can be considered as product development. So it is not Industry 4.0 as such which is required, but it is basic engineering, basic dynamics, basic solid mechanics, and finite element analysis, and these things which are required for product development, product improvement. But cyber physical systems as such, Internet of Things, cyber physical systems are not for these fundamental issues. Your question is more fundamental on product development. Product development is hardcore area, and that is hard work also. You cannot ignore the basic and fundamental work that needs to be done. And it's a very relevant question. If I talk about bogie design, it's a very relevant question that Where are the bogie designers in India?
Exactly, sir.
No, we don't have them.
Sir, this is Ravi Kumar, sir. I am taken over recently as the director of this institute. Hear me?
Namaskar, sir. Namaskar,
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 sir.
namaskar.
I have just one small question, sir. Like Industry 4.0, we are tracking the machine utilization and its productivity and things like that. But can I also track the men who are working on this machine for their attendance and things
Yes,
like that?
yes, yes, yes,
Yes.
yes, yes. Through the HMIs that I had shown, human machine interfaces that I had shown, I am not sure whether you were there that time or not.
Yeah, Mr. Yes.
I'll start sharing again. I think I'm stuck here. Anyway, what I difficult to go back to that slide somehow. We had these pads.
And as I understand, the operator on the machine is stackable, but in general, all the operators,
Yeah.
all the other staff
Can you see
who are
this?
working in the workshop.
Yeah, they are they can be trackable through this operator device.
Okay.
Can you see this?
Right, sir. Right, sir. Yes.
Yeah, they are trackable. These devices would industrial device would cost around about 90,000 to a lakh each, rugged devices.
Yes, yes.
And they can be customized, in fact. So for a mining process, it is very important.
Right now, in the Indian Railways, we have done a lot of Industry 4.0 in the terms of tracking of the machines is concerned, especially the CNCs.
Right.
Now we don't have this HMIs. I think
These HMIs can be integrated with other things in the process.
So, right. Thank you.
This is very good. This is powerful, very powerful.
Right. So thank you. Other questions?
Okay. So we can have one last question from the
Sir,
audience.
good morning, sir. Sir, good morning, sir. Sir, I am DME Samastipur. Sir, am I audible?
Yes, you're audible. Please continue.
Sir, my question is about the lab view. The problem here is of industrial automation. So this industrial automation is using the lab view for coding purpose. So is this component dependent, or these are going to work for any type of component?
This LabVIEW is now the industry standard for practically 80 to 85% of industrial machinery. More than that, in fact. So you have the acquisition modules for most of the sensors and most of the
Components.
controllers.
Sir.
Most of the controllers. If not, you sensorize. When you put in your own sensors, you can write your own data acquisition code also. So rather than doing it in a very basic language of writing the controllers for each machine, we are working at a higher level of and only the person who writes the code requires LabVIEW. Others, it is just the execution file that is important. So it is better to adopt the industry standard, which most of the others are also doing. Adopt that industry standard rather than reinventing the wheel, because otherwise writing your own code will never be possible. In fact, millions of human hours have already gone into development of this.
Thank you. So so that brings us to the end of the Q&A session. Thank you very much, Dr. Vyas, for taking time out of your busy schedule and agreeing to address us on the topic of Industry 4.0. We wish and hope that in the near future, you will be a part of IRIMEE's endeavor to disseminate knowledge across Indian Railways. Thank you very much, sir. So that, dear participants, that brings us to the end of this webinar session. I thank you all participants for joining the session, and I wish you all have a very good day. Thank you.
Thank you.